Hello and welcome to this 8th session. Last time we were looking at helium and specifically the importance, because of course it's a multi-electron atom now, looking at the importance of electron spin and also looking at angular momentum coupling with other sources of angular momentum. So for example, the two spin angular momenta on each electron coupling to a total spin angular momentum. And what we're going to do this time is we're going to look at some other atoms, looking at the spectra of multi-electrons atoms more generally, with several others beside helium that we'll look at today. And you can see here that we've actually got some lamps in action. So some lamps from the department. You can see we've got these little handheld spectroscopes which we've mounted up. And so in fact through those spectroscopes, just using a mobile phone actually, you can photograph the line spectra, as you can see on the screen here. Now, a bit about these gas discharge lamps. I'd always kind of assumed they were just a simple thing where you kind of create a plasma in the lamp, and then that's to say you strip electrons off atoms, and then the electrons recombine with the atoms, drop down the energy levels, and give you your emission spectrum. But actually, they're rather complicated things, these lamps. And in fact, the pictures up on the screen there show you there's quite a lot going on. So you can see on the top picture there, we've got current on the x-axis, and you see it's a logarithmic scale there. So on the left-hand side, we've got these absolutely tiny currents, and so hence the dark discharge. There's not nearly enough light off this to notice it. And then once you get past that first dotted vertical line there, there's enough current for you to see the light coming off, the so-called glow discharge. And one thing that's quite interesting about that, you can see, is that as the current increases, the voltage goes down, and so this implies quite a significant drop in resistance, which can be quite significant. And you can see then we get this critical point where the next vertical line comes along, where it turns from a glow discharge to an arc discharge. So these arc discharges are associated with much larger currents. So the arc there, a bit like a sort of lightning strike, you've got essentially, I think, like a narrowed channel where you've got loads of plasma, and essentially you generate quite a large current, and it gets very hot, and the heat from that as well generates even further emission, thermionic emission. So, and in fact, that was how the kind of original discharge lamps worked, I think, through arcs. And then down at the bottom there, we've got actually a DC type of lamp. So you can see you've got a cathode on one end and anode on the other end. So yeah, as the title says, two modes of operation. And so we can consider there to be two types of discharge. So we've got the glow discharge here, where you've got lower currents than the arc discharge, lower temperatures, lower pressures, lower power density, higher resistance, higher voltages. And so these are the sorts of classic discharge that we see in lighting and advertising. And so the arc discharge there on the red bit on the far right of the diagram, this effectively representing very much the opposite of the glow discharge. And so yeah, originally done with graphite electrodes. But, the electrodes take a real hammering, and they have a fairly short life. And onto some more detail here. So this point about we saw with the glow discharge there, that as the current increases, the voltage decreases, and so we get a drop in resistance. So as the resistance goes down, you can expect more current, and then with more current you get a further drop in resistance. And so there's a danger of a kind of a runaway effect here, and so you may suddenly get very, very large currents, and you could damage your lamp this way. And so in fact, one of the things that makes these lamps quite expensive is they need quite a lot of supporting electronics to prevent these sorts of current spikes, with using a so-called ballast. And so this is using an inductor. So the inductor here, this involves a current going around a coil and inducing a magnetic field. And so when you get a sudden change in current, effectively that would look to create a sudden change in the magnetic field, and ultimately these changes in magnetic field are going to resist any further current change. So effectively it damps down the tendency for it to spike. DC rather than AC, this does have some advantages. So as I've pointed out here, if you've got one electrode that's always a cathode and one electrode that's always an anode, you can then start optimizing the electrodes for their different functions. So for example, it might be convenient to have a cathode which can handle a high temperature and have a material with a low work function. And so this will make it easier to get electrons off if there's some thermionic emission. And then looking at this picture at the bottom right there, we've got these dark spaces, and so this could reflect the fact that if you like, the ions and the electrons are somewhat separated, or perhaps if the electrons don't have sufficient energy to ionize the atoms, that could account for it as well. And so you often see fused silica glass with these things. Silica glass is very useful for spectroscopy because it lets ultraviolet straight through, and it's good at withstanding thermal shock. And I think typically aluminium oxide is used rather than silicon dioxide with sodium vapor, as it's sort of more resistant, doesn't discolor. Now on this slide, rather like before, we see that these gas discharge tubes are really not quite as simple as we might have thought. So we have some fairly complicated behaviour being illustrated on this graph here, and on the y-axis we've got the discharge voltage, and so that's labelled V sub B. That'll be B for breakdown voltage. And on the x-axis we've got P times D. P is the pressure measured in torr, that's sort of an old-fashioned way of saying millimetres of mercury, and D is the distance between the electrodes in centimetres. And so you can see here that the dependence of this P times D quantity on the voltage isn't totally simple. And so if you want to minimise the voltage required for discharge, you can see that there's this kind of sweet spot. It's not just a question of making the product of P and D just bigger or smaller. We need to be at this optimum value. And so you can see there's some kind of compromise has got to be met there. And so what's going on here, as far as the pressure of the gas is concerned, if there's exceedingly small pressures of gas, then you're not going to get many collisions between electrons and gas molecules, which would suggest that you want to increase the pressure of the gas somewhat. But if the pressure of the gas gets too high, then collisions become extremely frequent between electrons and these gas molecules. And if the collisions are extremely frequent, then the electron won't have had time to accelerate to a high enough speed and to gain enough energy to cause the ionization that's required. And that's why we need just a kind of optimum pressure. And you can say a similar thing about the distance between the electrodes. So you might imagine that you would want a very short distance. So the shorter the distance between the electrodes, the more intense the electric field. But see, once the distance starts becoming very short, then you'll be up against the fact there'll be very few collisions with gas molecules in a very short distance. And again, the electrons won't have had enough distance to really accelerate up and to gain a lot of energy. And there's also a thing called the mean free path, which is how far particles have to travel before, on average, they have a collision. And actually that's rather longer for electrons than it is for atoms and molecules, with the electrons being much smaller. So it's about a half a micron for electrons, whereas it's more like a tenth of a micron for molecules. So there you go. So there's a kind of sweet spot there for the distance between the electrodes, also for the pressure of the gas. And a few more details about the way these lamps can work. So one mechanism of getting these currents started is heating the cathode. And so if the cathode is really hot, say heated to 1000 degrees, you can get this so-called thermionic emission of electrons, where the combination of the heat raising the energy of the electrons combined with a large potential difference between the cathode and the anode, eventually you can get a stream of electrons just coming off. And this stream of electrons will smack into gas molecules and ionize the gas molecules. And once you've ionized a gas molecule, you'll have turned it into a cation, because the electron collision effectively will knock another electron out of the molecule, leaving a positive ion. Then that positive ion is going to get accelerated back towards the cathode, and in fact that ion then might just smack into the cathode and cause this further emission of electrons. If you don't heat the cathode, you're not going to get that kind of thermionic emission, but what can happen is if you have a high enough positive voltage at the anode, you could end up effectively ripping electrons off nearby gas molecules and turning them into cations. So again, if you've got thousands of volts, the anode there can ionize the gas. So there we go. This is referring here to the graph that we were talking about earlier. And so yeah, this is the so-called Paschen's law. This is the same Paschen, incidentally, that we see in the Paschen series. You might remember from when we're looking at the hydrogen spectrum. Like, so when you go down to the first shell, that's the Lyman. The second shell is the Balmer. Then the third shell is the Paschen, isn't it? And then this bottom picture on the bottom right there, this is something that you often observe in these glow discharge tubes, these so-called striations. So you can see it looks like they're these sort of little blobs of extra intensity of light there. It's like beads of more intense light, these so-called striations. And so there's something going on here. I mean, it looks like a kind of oscillation going on in the plasma, and another thing that I think may potentially cause it is kind of getting step changes in the electron energy. In fact, we'll look at this next time, the so-called Frank-Hertz effect. The electron energy can kind of periodically oscillate as it can, at crucial energies, kind of deliver energy to atoms of gas. And then I guess the final thing to say is that when we produce these cations, when you've got a species in the gas phase which has lost an electron, at some point it's going to recombine with an electron. And as it recombines, that electron is going to kind of drop down the energy levels in a sort of cascade. So it won't, the electron, you'd expect the electron ultimately to end up in the lowest available energy level in the atom. So the atom, as it were, reaches its ground state. But it doesn't necessarily do that in one go. It can cascade down several steps. And with each little step, there can be a frequency of light associated with it. And that's why when you look at the emission spectra out of these lamps, you see loads and loads of lines. And that's because as the electrons are kind of relaxing back to the ground state in the atoms, they're dropping down all sorts of different energy levels in lots of different atoms. And so when you put them all on top of each other, you get really quite a large number of frequencies usually. So I thought I'd say a little bit about the spectroscopes and how we resolve these line spectra in the first place. So in theory, you could separate the different frequencies of light by passing them through a prism, for example, but in practice we're using a diffraction grating, and which is what we have in the spectroscopes. And in fact, the little picture on the top right there illustrates what's going on. So you can see where it says bright fringe, this is where you're going to have constructive interference by rays, which you can see from the two different slits. The lower ray is actually going to have to travel a bit further than the upper ray to get to the screen at this angle theta, and the difference in the path length for these rays is lambda. That's to say the wavelength of light. And so when the distance is exactly lambda, then ultimately there'll be a constructive interference between these two beams, as you've got crests overlapping with crests and troughs overlapping with troughs. Whereas you can see on the picture on the right there, the difference between the two rays is now half a wavelength. And so then this would give you the destructive interference where a crest overlaps with a trough, and this would be a dark fringe therefore on the screen, and so you get these light and dark fringes being formed. And these are the equations here for diffraction. And so you can see here with this first equation, n lambda equals d sine theta. It does show you therefore that the wavelength of light is an important property, and so it's going to depend on the wavelength of light, the position of the fringes. And also you can see there that you see in the picture we've got a difference of, for example, one wavelength between two rays of light, but really it doesn't have to be one wavelength, it just has to be an integer number of wavelengths. And the more wavelengths that are involved, in fact the higher the so-called order of diffraction, and that number of n kind of counts the order. So in the example in the picture there, n equals 1, where it's 1 lambda difference, but we'll see higher orders as well in there. So yeah, in the equation then, so lambda for the wavelength, d being the spacing in the grating, theta the angle of deviation of the ray. And then if you look at it from the sort of screen point of view, if the screen is a distance d from the grating, and y can be the distance of the diffracted ray on the screen from the undeviated, so theta equals 0, sort of 0th order line, then we have this expression involving now tan theta, and in fact we can combine these together and get an expression for y being the distance between the fringes on the screen. So you can see that the distance between the fringes on the screen is going to be here, all other things being equal, proportional to the wavelength. And so this is how we're going to see the wavelengths get separated out on the screen. And so you can see here we've got this diffraction grating being shown on the right hand side. There's 600 lines per millimetre. I think that's fairly standard. In fact, before we get into line spectra, I thought I would just contrast it with an incandescent light, because the other form of light that we typically see is just from an extremely hot object. So objects naturally emit light as a function of their temperature, and in fact what we've got on the screen here are the black body spectral curves that we get, and it shows you the dependence of temperature. So you can see there where visible light is marked on the diagram. This indicates that you really need to be getting very hot before things are visibly glowing. And so you can see that the coloured line there, that's sort of 5,700 odd Kelvin, that's going to be representing the sun. And so you can see the sun has got a fairly level line through the visible spectrum there. So that accounts for the roughly white colour of the sun. So yeah, this all follows from the Planck's law for black body radiation. So as I say, when things are very hot, so this could be the filament, the tungsten filament in a light bulb, or from the sun we get this continuous spectrum as opposed to discrete lines. In fact, one thing that I thought would be worth mentioning here, and it kind of combines line spectra and these continuous spectra, are the so-called Fraunhofer lines. So Fraunhofer, early in the 19th century, was looking very carefully at the spectrum of light from the sun, and he noticed that as well as there being this continuous spectrum of light, there were these dark lines appearing in there. So I think he realised that these dark lines must represent the line spectra of atoms in the sun absorbing characteristic frequencies. And in fact, comparing the line spectra of elements on Earth with the lines in the solar spectrum, he was able to identify elements in the sun. And in fact, in these tables on the screen here, you can see several elements being identified. And there's also a few cases actually where there are lines from oxygen in the atmosphere, but most of them are from elements in the sun. And it's quite an interesting story. Obviously, we were looking at helium in detail last time, and I think, as I mentioned last time, helium was actually discovered in the sun before it was discovered on Earth. And so it's because they found this faint line about 5,876 angstroms, and they realised there was nothing that they knew about on Earth that was giving that same wavelength. And so they boldly postulated that there must be an element in the sun, Greek helios for sun. And so I've just made the point here that, of course, they had no idea of knowing if it was a metal or a non-metal. They called it helium, and the suffix "-um" is associated with metals, and they kind of guessed it was probably a metal because most of the elements in the periodic table are. Of course, later on, when it was realised it was a noble gas, you'd have thought they might have changed the name to helion to fit with neon, argon, krypton, xenon, but of course the name had stuck, so they just left it as it was. So now I thought we could look at a few more examples of spectra. And so, in fact, looking at this neon spectrum here, what we find, if you look at the line spectra beneath, you've got that central line in the middle there. And so that central line is not split up into different frequencies, that 0th order line. And so you've got just the overall red colour of neon there. But then to the right and left of it, what we're seeing is the first order in diffraction. And you can see that the kind of bluer lines in the spectrum are closer to the middle and the redder ones are further away. And that's consistent with the equation we had before, where y was the distance from the centre, and that distance was scaling up with wavelength. And obviously the red light's got a longer wavelength, so it's a further distance from the middle. So that explains the orders of the colours there. And you can see that beyond those first order lines, you've actually got a set of second order lines as well beyond that. So this is why we see these kind of multiple sets of lines kind of symmetrically arranged around the middle. It's these different orders. And so looking at the neon spectrum there, this is actually very complicated. It's actually quite a headache trying to understand what's going on here. Perhaps the first thing to say is that, again, when you look at these configurations there in the table, nowhere do we find the ground state. So of course the ground state for neon, of course noble gas configuration, 1s2, 2s2, 2p6. But in fact the transition's going down to 2p6 actually in the ultraviolet. And so we see these smaller energy gaps in the visible. And so you can see, look, comparing the ground states on the left and the excited states on the right, they both involve 2s2, 2p5, where the final electron has been excited out of the second shell, but it's just moving within the third shell. So in that first transition it's dropped from 3p to 3s in the third shell, while the second shell still isn't completely full. So it's easy enough to see what's going on there with the configurations, but actually what's really complicated is when you look at the actual states of the electrons, because you can see on the right hand side some very bizarre, unfamiliar looking notation here. And so actually what's going on here, which is a bit bizarre, is that you see, because the 2p electrons and the 3s and the higher energy electron, because they're in different shells, again, they're not actually interacting with each other that much, but like I mentioned in the helium case earlier. But what we do see a bit of in neon, and this is something that we associate with the higher atomic numbers, is you can see a bit of interaction between the spin angular momentum and the orbital angular momentum on an individual electron. So when we look at that first transition, so the ground state there, so effectively you see we've got this, I suppose you could say there's an unpaired 2p electron, and so we've got a 2p there combined with a 3s. But what's happening is that the spin of the electron, that spin half, is coupling with the orbital angular momentum, which would be 1 in the case of a p electron, and so the orbital 1 and the spin half are coupling together to give a resultant of a half, and that's written as a subscript, and that is given the symbol J for total angular momentum. So it's the kind of resultant of the spin and the orbital coupling together to give a total resultant, little j. And then the other one, 3s half, well, you've got an orbital angular momentum of 0, a spin angular momentum of a half, giving you a total angular momentum for the other electron of little j2 equals a half. So we've coupled up the angular momenta differently in this case, and so in that bottom state we've got two electrons where each electron has a total angular momentum of a half, and then at this stage we combine the two electrons together, and the two halves, the two little j halves coupled together to give you a capital J total angular momentum of 1. And so you can see that bottom level has got a J equals 1 attached to it. And then on the upper state there, it so happens that all these total angular momenta couple up to 2. And in fact, when you look at all these lines, you see that the difference in the total angular momentum is equal to either 0 or 1. And this is consistent with the single unit of angular momentum coupled by the photon vector coupling with these totals, which means the angular momentum will either be unchanged or changed by plus or minus 1. And so, yeah, just a comment here about the different coupling on the electrons. So yeah, it's actually loads and loads of lines in these spectra. Quite difficult to sort of unravel it all. So in fact, now going on to argon, another noble gas, and a similar sort of picture in a way. We've got, again, we see, looking at the transitions, that we never drop down to the ground state, 3s2, 3p6, but we've always got an excited electron in the fourth, dropping down to a level in the fourth shell. So in fact, all these transitions here are actually within the fourth shell. So that first one is going from a 4p orbital to a 4s orbital. And actually we see a very similar kind of thing here with the coupling of the angular momenta and the capital J's. It's just like we saw with the neon case. And in fact, one thing which I was didn't quite get as far as saying last time is this business of the p5 configuration. So I mentioned before, there's an uncoupled electron, but strictly speaking, when you look at the configuration as a whole, the p5, a slightly more helpful way of looking at it, in a way, a sort of shortcut, is rather than considering all 5 electrons all coupling with each other to a resultant, you can also treat it as if it's got like a positive hole in an otherwise full subshell. Remember, we were saying last time that in the case of full subshells, all the angular momenta add up to 0. So a full subshell, remember, is kind of invisible with no angular momentum associated with it at all. So what's rather neat is that you can kind of treat P6, as it were, a bit like you would P0. And so curiously, P5, those 5 negative electrons, actually behave the same as what a single positive p electron would behave like. And in fact, this is how we tend to look at a p5 subshell. We consider it as a single positive electron. And that's why we've got these labels. Actually, we call it 3p a half in these electron configurations. That's effectively how it behaves. And so, yeah, of course, we meet positive holes, don't we, in semiconductors? Like if you have a gap in the valence shell, if you excite an electron up to the conduction band. Yeah, same sort of idea. And onto Krypton now. So again, similar sort of thing to before. We never get quite to the ground state. We've got these emissions really all with the excited electron up in the 5th shell, angular momentum coupling in the same sort of complicated kind of way. And so just a bit of a reminder here that of course the photons do carry a unit of angular momentum, which we can consider as a vector. And so that's why we have this sort of vector addition, and how, for example, you can see here in the bottom transition there, you're going from a j equals 2 state to a j equals 2 state. And so you can couple a vector of length 2 with a vector of length 1 to get another vector of length 2 when you have them in a kind of triangular arrangement. So you can have a delta j equals 0 transition and not violate the law of conservation of angular momentum. But the point is made here that you may be able to have delta j equals 0 in the general case, but in the specific case of j equals 0 to j equals 0, this is forbidden, because there's no way you could combine the arrows. You would just have a single arrow of length 1, and there's no way that you would couple j equals 0 to j equals 0. So that's the one case where delta j equals 0 is forbidden. And onto Xenon now. So I'm afraid we didn't have our own lamp for Xenon, and so I've actually just at the bottom there, I've just published a spectrum that you can get on the internet. So again, you can see absolutely loads of lines there. So it'll be like a real big job to interpret absolutely every one of those lines. And so on the screen here, I've just put in the most intense lines. And so curiously, you can see here that actually the most intense line comes from Xenon Plus. So of course, as you go down the noble gases, the ionization energy drops. And so as you get down to xenon, it's relatively easy to ionize. So you start to see quite a lot of ionized forms of xenon. So basically the xenon would have been ionized to like a 2+ in the plasma, and then an electron would have combined it with that, and then formed an Xe+ and dropped down the energy levels, giving you the emission spectrum of Xe+. And of course, the other thing is, not only is it low down in the noble gases, having a lower ionization energy, but of course xenon's monatomic as well. So you haven't got to worry about breaking any chemical bonds to get it into its atomic and ultimately ionic state. So we've got the nitrogen spectrum up here, and so again we've got these a few assignments there from the visible part of the spectrum, and again we're not seeing the ground state at all, which would be 2s2 2p3, and this time we don't see the same coupling scheme that we did in the noble gases. So we've got this these so-called LSJ levels. So what we've done here is we've added up all the spin angular momenta for all the different electrons, all the little s's or ms's, and ultimately determined a capital S, the length of the overall spin vector. And then of course you might remember we see this as a superscript of 2s+1. This is the spin multiplicity. And then likewise we combine all the orbital angular momenta of all the different electrons, and ultimately these get expressed as the capital L quantum number. But just like we do with the electrons in, say, in a hydrogen atom, the subshells which represent the orbital angular momentum are given a sort of historical letter: S equals 0, P equals 1, D equals 2, and that's what we do here with the capital letters. So capital P here denotes the total orbital angular momentum, capital L equals 1, for example. So what we've done here, we've got an overall spin S, which we show as the 2s+1 superscript. We've got the overall orbital angular momentum, capital L, which we represent with one of these spectroscopic letters. But what we're doing here, which we do really once you get past helium, you start doing this with atoms, is we then couple the S and the L to give a total resultant. So you can see in that top level there, the very first one is 4p, where you'd pronounce that quartet P, and then 5/2, the subscript. So you can see that quartet there, that quartet being the spin multiplicity, that's your 2s+1. So actually the capital S in this case must be 3/2. And so that 3/2 there, that's going to represent 3 electrons spinning parallel. So you can see in our configuration there, on the ground state configuration in the first row, we've got 2s2, well of course that's a closed subshell, so that's kind of invisible. Then we've got 2p2, 3p1, and so those electrons must all be spin parallel. So you kind of expect 2s, we normally think of 2p2 as those electrons being spinning parallel in separate p orbitals, and then clearly the 3p1 there would be spin parallel as well. So we've got 3 lots of +1/2 for our m sub s quantum number for each electron. So the total spin is 3/2. So when you express that with the spin multiplicity, 2s+1, that gives you the 4 as the superscript. And then again, what we see here with the L equals 1, that goes to show that the total orbital angular momentum in this case is equal to 1, and the subscript there, 5/2, 2.5, this is telling us that the 3/2 from the overall spin and the 1 from the overall orbital angular momentum, the 3/2 and the 1 there are going to vector couple to give us 2.5. That's the 5/2. And so actually this is something that we do associate. When you see a fraction there for J, that's something you'd associate with an odd number of electrons outside closed shells. So there we go. They're the most intense lines for the nitrogen spectrum. And so I've made the point here that generally speaking, where we have these 2p electrons, where you consider the p2, if you like, in isolation, they would be spin parallel. And so that spin parallel state would have to be triplet P. So we've got an electron, if you like, in the sort of, if you like, the +1 and in the 0 ml orbitals, giving a total L of 1, and the S equals a half plus an S equal, well, the MS equals a half, MS equals a half, adding up to 1, ultimately giving us our triplet state where capital S equals 1, shown as the multiplicity. But we do have an exception in here, and that is that in one state in particular, and so this is going to be on the third line down on the right hand side, the highest state, that actually involved the 2 electrons in the P2 subshell being singlet D. So singlet there means that they are spin antiparallel, so the total spin is 0, so the spin multiplicity is 1, and the D represents the fact that both of those electrons are in the ml plus 1, if you like, orbital, where the total ml then has gone up to 2. And just a final point here to do with the fact that we do see some interesting colours out of nitrogen in aurora, like in the northern lights, and so we see some blues and reds. But one of the interesting things about nitrogen is that because we have this extremely strong triple bond, there isn't actually quite enough energy in those aurora to get it down to atomic nitrogen. And so we tend to find that the diatomic molecule, or the ionized form of the diatomic molecule, being the species from which you get these emissions. Now the oxygen spectrum. So yeah, I haven't got the actual lamp for this unfortunately, but again, I've got a spectrum off the internet down at the bottom there. And so again, we're seeing these lines. We've got even number of electrons this time, which is why we don't see any of the fractions in the J's that are quoted. Same sort of coupling that we saw with the nitrogen, but curiously we're seeing a bit of O plus this time as well. And so I think this reflects the fact that, you know, less, I guess, it's more easy to break the molecule up into its atoms and ultimately to ionize it. Of course, oxygen's got a lower ionization energy than nitrogen, hasn't it? Because you've got the paired electron in the 2p subshell. And so, curiously, in aurora, so in the northern lights, the colours that we get here are actually from this atomic form of oxygen, from the ionized form of oxygen. And again, sort of relating to the fact that it's easier to break down the molecule to atoms, easier to ionize the atom. And interestingly, you get these long-lived forbidden transitions. So if a transition's forbidden, then, you know, there's less, as it were, sort of driving force for it to emit from the upper state to the lower state. And so it often sort of tends to bleed down fairly slowly from one to the other, given these long-lived transitions. Then onto chlorine, so not quite so much to say about these. We haven't got the lamp, unfortunately, just published spectrum. So again, you get a mixture here between the atomic state and the ionic state, giving you these emission spectra. Then again, got bromine now, just following a similar sort of pattern. We just got the higher shells, obviously. Then onto the iodine spectrum, similar sort of thing. And we'll just finish off with cadmium, actually. This is quite interesting. So cadmium is the element under zinc in the periodic table. So zinc, of course, that's 4s2 3d10, isn't it? So when you get down to cadmium, that'll be 5s2 4d10. And so when you look at these transitions in the visible here, the 4d10 remains untouched. It's really what's happening is from the 5s2, one of the 5s electrons is getting excited up to a higher orbital, to a higher subshell, and then it drops back down, but rather than going all the way back down, back to 5s, it's dropping down to a higher level. So we can see it's dropping down to 5p in the first two transitions there. And that's again because if it dropped back to 5s, it's probably going to be out of the visible, so which is why we wouldn't see it. But it's quite a beautiful glow, that cadmium glow. And curiously, I think you sometimes see a bit of a blue tinge when you burn zinc. So it's a bit of a hunch, because zinc and cadmium are in the same group in the periodic table, which means there's sort of similarities in their chemistry. For that reason, cadmium is probably quite a likely candidate as an impurity in a zinc ore, where the sort of geochemical separation processes haven't completely managed to separate the elements because of their similarity. So I think, cadmium may account for a very slight blue tinge that's sometimes seen in the burning of zinc.